you. Hello. Hi. Good morning, everyone. It's good to be back here. So last time I was here in the winter, and now it's the summer. I'm coming back again, and I like to actually kind of reporting the status of what Tenstorrent is doing. So what I actually realized after joining this company is that AI is moving so fast, right? So the company, like I'm working for Tenstorrent, is also experience a lot of different transition, how the company strategize, position ourselves to addressing the technology demand in the AI, and also many different fields, right? So today's topic is more talking about how important is the RISC-V technology in the Tenstorrent strategy of forming the AI computation and general computation. So what I find really interesting is that RISC-V even is starting as an open source architecture for the processor, but actually are moving along with the AI development in the world, right? Become a very strong technology behind this very important movement in the human history, which is the AI revolutions. So I don't have to explain this slide. The AI is everywhere, right? So it's forming this digital transformation for the whole world. Like I say, right? So the AI, the most important thing AI can bring into this world is about its capability to personalize the technology for yourself. Like you have a question, you ask ChatGPT-3 and then ChatGPT-4. You have to Google it. But now the machine, because they understand the natural language, they can actually put in, answer the question for you based on your question, personal question, and you can continue in the engagement with the conversation. Like yesterday, I was looking at the map in Japan, and then I asking the ChatGPT the question saying that, oh, can you actually form in the PDF picture of my route from here, my hotel, and then going to somewhere else? You're actually creating that for you, right? So it used to be that technology has to be like you talk to people and you write in the note, you put in the picture there, you routing together, but now it's all automatic. The similar thing will happen in the medical. They can personalize the drug for you. They can even personalize your kids' education in the future. So it's going to be everywhere. So it's very important technology. So I was creating this picture for the last presentation. I talk about like when is actually really the AI revolution happen. It happened on the combination of a couple of things, right? So one is the availability of the wide area of the data available because the mobile phone, revolution, right? So that's one thing. And then the other thing is actually the available of the technology is enable you to build in the computation you need for the accuracy of the AI inferencing or training you want. And that happened on the 2012, the time actually mobile computing go around 4 years of the revolution. And you can see a fair amount of data available in the data center and it's stuck in training the data. The neural network technology, when I learned at school, right, it's already like 1967, 1968, where people talk about it. But the availability of AI today is just because of combination of the widely available data and also the technology, right, semiconductor technology. And one thing actually interesting on this graph is that RISC-V technology is starting on 2010, right? So it's kind of colliding with this AI revolution happening and RISC-V starting developing this architecture. And what's eventually happening is that, like Tenstorrent founded in 2016, right? So they are looking at the technology, CPU technology that enable to control the AI accelerator. And then they find this open source technology, RISC-V, is actually very interesting, right? You can use using the existing compiler, you can change whatever you want, and it's very simple to do, right? Because it's a RISC-V, the ISA is pretty simple. So we actually design a lot of in-order processor, single issue processor, become a control processor for our AI processor. So what this trend is actually show you is that because exponentially grows on the data requirement, computation requirement, we are predicting that AI computation need to be everywhere, right? So that's mean the technology actually behind this AI computation is also required to be scaled itself to the different PPA requirement. So we are predicting that AI computation will be everywhere. That's why AI technology behind there's a RISC-V process technology, it need to be also scaled accordingly, and Tenstorrent is doing that. So this is just repeat what I say, AI will be everywhere, like Tenstorrent is engaging many different partnering company in the world, including government, big enterprise, right? So it will actually contain client device, right? So we are working with a consumer device company, and then we are working with the edge company, we are working on autonomous driving company, right? And then we are working with the data center for ourselves. And all this technology will actually enable the technology AI computation everywhere, the vision we actually have. So that the RISC-V technology play actually a very crucial, important role behind this. So why the RISC-V is an important technology, right? So it has 4 different attributes. One is the scalability, right? Like I say, if you actually license the ARM architecture, right? So when you license the architecture, you say, I want to modify the ARM, building some ARM CPU processor. You have to basically tell them what you're gonna do, how you're gonna use it. If you have make any change on the architecture during the extension, you have to get their permission, right? However, RISC-V, because it's open source, they have a solid foundation definition on the architecture specification. But on the top of that, you can innovate whatever you want. So that scalability, what I mentioned here, is that enable you to build so many different PPA processor, right, to doing the thing you want to do, right? The second is the extensibility, right? So you can extend the ISA to supporting the instruction you like to have for particular application, for particular power optimization, for particular, performance requirement. So that extensibility gives you the flexibility to address this huge computation need, right, for the AI. The third one is the efficiency, right? So RISC-V is actually open source, and then it started later, so it doesn't have the architecture burden of like ARM processor, ARM instruction set, which started maybe 30, 40 years ago, or x86, right? So it's much cleaner, right? Agree, like even now, like people start adding on top a lot of different extension, right? So I was talking to the people on RISC-V organization. We have to be really careful doing that. Otherwise, we will carry so much burden. Later, we become x86 and on. And also, it's stable, right? So what's mean the stability is that you as a company or a technology innovator, you want multiple source of the IP coming from different places, right? To enable you have the stability of the supply. This is crucially important. Like, if I'm designing something I'm using ARM, my only source IP is coming from ARM, then there's a potential risk that they can do monopoly, kind of position and asking any price you want. So that would jeopardize your business position, right, in this world. So the RISC-V, because it's open source, you can take the core from Anders, right, for the CEO is here, and then can take from Tenstorrent, you can take from Sci-Fi. So that stability of the supply chain for you is actually very crucial for your future development. So Tenstorrent, I joined Tenstorrent about 3 years ago, right? I'm from Apple. And then I started working on the RISC-V high-performance processor, right? So what's interesting is that originally we wanted to use in RISC-V, general purpose compute, to combine with the AI, right, together. But what I'm very interested in is that once we talk to customers, there are so many people coming to us say, hey, can we license your technology for doing this, for doing that, right? So the whole conversation driving into the IP discussion and then also the ecosystem discussion, because for the particular sector, right, we are going after, there has to have the software ecosystem support there, right? So that's where the conversation for us, going with our partner, is about what kind of PPA you want, what kind of software ecosystem you have, right? And going to address wide variety of the market, we actually going after like autonomous driving, data center, or even consumer space. You can you can look at the stability, right? So currently, all the RISC-V company in the world are actually providing the solution for the RISC-V IP. Some of them may be a system design company, some of them provide the IP only. But the diversity of the potential IP source is much, much better than ARM, right? So this is a critical important thing you guys have to remember. When you're choosing an architecture for your project, you have to choose, make sure that the supply chain, the IP supply chain is there so that you will not controlled by the company, by one single company for your future direction. Tenstorrent as a technology company, right? So we have a very good engineer there. Like we have founded, our CEO is a legendary chip architect, Jim Keller, and then he hired a lot of people from different company. I used to work with Jim for like 15 years, right? So in miscellaneous company. And we have many people coming from Tesla, from Apple, from AMD, from Intel, right? We formed this company. And this company is actually specialized not only on the AI now, right? So we also has the CPU IP, and we also, most important for the AI market, we have open source, you know, the software ecosystem to support our AI hardware. So the company now actually selling an IP, like I say, AI will be everywhere. And very important thing is that most people, when they look on the AI in this market, they want the AI IP to supporting their effort on the particular segment market they are enter, right? And secondary is that they want a very mature chip design technology. And Tenstorrent is actually developing the chip design, you know, technology actually licensed to people. And then like we have the project in Japan, we license our chip technology for the project, jointly developed some edge inference project. We also have the chip for our own, right? We are building data center device. We are making the chip for the, server box, AI server box, or highly scalable system. And then we also has the, most importantly, address the market in data center, automobile, and then client device. And then this is the partner we actually engage in. It's tell you like how widely engaged we are in the war with a different company, and they all need the RISC-V technology and AI technology, right? So this open source, technology is actually what's becoming is that everybody wants to secure the future of their country, right? Economy security or national security in the country, or the enterprise want to secure their technology source. They will go into the open source, like RISC-V. And then we, Tenstorrent as a company, we open source our AI stack, and else in the future, maybe the AI hardware. It actually gives the people the stability feeling, or just talk about the secure of the supplying source in the future. That's why so many companies are interested in talking to us. And Tenstorrent actually got this very unique vantage point, right? Looking at very different wide variety of market, understand how we actually design our product to fit the different, product requirement between PTA need. So this is kind of repeat what I just say. The important thing you look at here is that we're providing the IP, we provide the chiplet technology, which will make the system scalable, and it can apply to many different design points. And also we have the server, right? We build a data server competing with the NVIDIA. And then we also have the open source software stack, which will have two different open source software that I will talk later. And then this is our silicon roadmap. Like we already on the third generation, right? The first generation is basically a single PCIe card form factor kind of design. The second generation, we started working on the scale technology called Wonghole. And we recently just released the AI server, right? 1 petaflop AI server, right? Using the Wonghole technology. We also had the black hole, which is just in the lab in testing using TSMC N6 technology. And I'm actually leading the effort, building the chiplet ecosystem for Tenstorrent. So in the future, Tenstorrent will go for chiplet. We have AI chiplet, memory chiplet, I/O chiplet, and also the CPU chiplet. All this composability actually enable us to address a wide variety of the need in the market, like autonomous driving, high performance server, HPC market, even some area in the consumer device. So when we talk about AI, you have to talk about the software ecosystem, and this is also tying to our application of the RISC-V architecture. So we have two different software architecture. One we call TT PyBuddha, right? So the PyBuddha is actually a high-level compiler. You can translate the PyTorch program to through the TVN to the data flow graph, and eventually compile and map into our hardware according to some optimization algorithm. So it's a simplified flow for the developer, right? So when you're using PyBuddha, they don't need to understand the hardware at all, right? So the hardware automatically take care of that, compile the program into your hardware. So there's a trade-off we have to make because the compilation speed and then the optimization point you have to make, the compilation result may not enable you to run at the highest performance possible, right? So however, it gives you a very fast way to validate your program and also make your program run on the machine and understand the program, behavior and correctness. And then we invented also the second flow is that we call TT Metallion. It's basically a metal flow. So you're writing a bunch of TT library, right? Metallion library, and you can call in, right? And using the C program, eventually you forming your algorithm can be forming and gel together using the C programming, right? So it's a very effective way to actually program the system when the performance is needed. So if you understand the hardware really well, which we have exhausted like tutorial because this is a Metallion flow, it's open source, we can actually train the people understand the hardware, and then you can spend a lot of engineer optimize the hardware performance based on your algorithm. So these two different flows is actually working differently. So PyBuddha is actually make you run really fast, right? Bring up your algorithm really fast, but Metallion flow is actually enable your algorithm has a very good performance with enough engineering effort investing in there. So our AI architecture is based on this architecture we call Tensix, right? That's the basic building element. So you see on the left-hand side is the IP. So you can take our Tensix, forming together using a NOC, right? Connecting together and forming an IP and then putting in your SoC system. And then we also using, of course, we're using that to build in the chiplet, and then chiplet can compose together and forming a larger computation units, right, in the one thing SIP. And we're using SIP and then connect together. You can see the Galaxy system in this example has 32 one-hole car in there and forming a larger computation device. So it's a scalable architecture, right? All the way from single IP to chiplet. Chiplet is also scalable based on your packaging technology. And then based on your system requirement, how many units, power consumption you have, you can form a larger scalable system. So it's a completely scalable technology. So you can see here, this is the Tenstorrent technologies that we're forming from the Tensix on the left-hand side. You can see there's a 5 embedded CPU, RISC-V CPU, very simple embedded RISC-V CPU in there. And you use that as a composer element to making a larger chip, right? Like in our example, we're using 2D mesh, right? Connect them together and forming a chip. And then we're using that chip, and then you can connect together using our Ethernet scale technology, forming a chiplet, right? And then later, we forming a Galaxy box, which you see the blue box in the middle, 32 chip forming together in the 4U units, and using the Ethernet scale technology, forming an even larger system. And in the future, we plan to build in like one exaflop machine, right, using this technology. So there will be a multiple boxes there, right? Our Galaxy box connecting together through the Ethernet scaling technology and forming a larger computation device. So what I want to dive into now is actually explain you in more details about how the RISC-V technology is using in our basic building element, Tensix. Right? So you can see on the picture here is our Tensix computation unit. If you really want to partition it, right, so you can partition to two parts. One is the communication subsystem, right, which is on the left-hand side and the right-hand side. So there's a RISC-V, this one, and RISC-V. And in the middle, there's a 3 RISC-V processor is actually using for driving the computation, right? So they are forming a kind of 2 disjoint system. One is forming computation using the RISC-V to control the data movement of the computation. And then once the data is moving to the local memory, you will actually using the computation RISC-V processor to perform the computation kernel, right? And then return the data by the left-hand side, by the right-hand side of that picture is that using to sending the data to the destination. So each of the processor here is very, very simple, right? Because we're gonna use them a lot. So I will give you an example of the scale, how many core in there. And this system has a special function. They don't need to be super complex. The important thing is that they're supporting the existing software stack. And also they are driving a very wide data computation, right? So they only performing not a complex integer operation, but they're performing a wide vector operation while maintaining some kind of programmability through the RISC-V architecture. So the RISC-V AI engine here has 2 parts, right? Like I mentioned. So it basically is forming a SIMD or MIMD engine. So it's a distributed computation engine, right? So some part of that is dedicated for the special. It's a very small and a simple, efficient processor because we use it a lot, like I mentioned. And it also has the vector engine and it's also matrix engine. The matrix engine is using for the driving a lot of square root special operation, and the matrix engine is using for the 10-6 computation. And then the important thing is that all this processor in there is using as a special control processor. They in general doesn't do a lot of scalar computation. So the task they have is actually doing whatever kernel telling to do, and then performing very simple issuing instruction, and then checking, for example, the FIFO, right? It's performing very simplistic function, so they're using a lot in the processor. So we're building that using the in-order processor. And also the other thing I talk about is that important thing is that we're using open source RISC-V toolchain, right? We can using the compiler, right, to compile, so we don't have to develop a special thing. So that's the nice thing about the RISC-V architecture in the AI. So this is kind of the breakdown. Like I mentioned, our tensor, right, it actually has 2 parts. One is actually the communication subsystem responsible for data movement. The other part is actually this 3, RISC-V processor in the middle manage the computation itself. So there's a one computation processor is basically taking the data, right, from the producer and putting in the local memory and reformatting before you send into the vector and the matrix engine. Right. In the middle of the processor, you're basically issuing the instruction, right, for the vector engine and the matrix engine, perform the computation and writing back to the local memory. And then the last processor, basically what you do is actually taking the last, computation from the processor and reformatting, right, and putting back to the memory from the destination region, reformatting, putting the format you want, and then sending out. So the communication processor, after the computation I just described is completed, right, you would do the sending of the computation and also receiving the next, computation packet from the producer. So you can see that this processor, the tensor design is basically a data flow computation engine element. It has a way to receiving the data from the producer, right, through some kind of communication mechanism, right? And then also sending the data out when it's complete. And in the middle has a 3 processor actually doing the reformatting of the data and also manage the computation required for this unit. So by doing this, right, so you have 5 different processors, they can do 5 different things, right? As long as they have a proper way to communicate to each other. And the nice thing about this is that we're also using the RISC-V instruction set, right? We have the RISC-V extension for our metric engine and tensor engine. However, all of the other things is actually compatible with the existing RISC-V toolchain. So the nice thing is that you can write in C program, you can write in whatever program you want to program this thing, right? Do whatever you want to do. So it's very convenient to do that. So you have the conformity to the architecture of the RISC-V, but at the same time, you also got the flexibility for the extension. So we also develop, so I just talk about is a very simple in order processor in the RISC-V, right? So that's the computation we have. And then it performs very simple operation. The pipeline is very simple. Area is very small. It's only perform simple operation. But we also developed this high performance RISC-V ASCON processor, which we are going to comparable to AMD Zen 4 and Zen 5 performance. So this processor is using for general purpose compute. So when everybody talk about AI computation, you have to remember that AI is a computer. AI computation is a computer, right? It's not just about acceleration. 5 minutes, okay. It's not just about acceleration. So you need the operating system, you need the security architecture. So general purpose compute is also very important. So that's why we're building this high performance RISC-V processor. So like I say, like the general purpose compute, our CPU can do that. Like in our Galaxy box in there, there's like, you know, the Zen 5 machine, right, in there doing the host compute. But for us, we can using our in-house developed CPU to replace that. That's $7,000, right, cost actually for our box. So we can actually replace that and make the system cheaper. So talk about hosts, right? CPU hosts, there have to be operating system support for the engagement we have. We see Android start maturing, and cars, autonomous driving system, operating system start maturing. And all the places we see a huge amount of effort porting the existing software stack, right, to the RISC-V. We also imagine a CPU, right, general purpose compute CPU in the future will be all part of the AI computation graph, right? So in the future, we actually see for the symbolic AI computation in the future, you actually have sub-symbolic computation using our AI accelerator, while you have the symbolic computation engine using our RISC-V CPU together. So when we're actually using this, building a heterogeneous compute system using the chip that has terabytes of bandwidth actually communicate with them, right? This is actually forming a very quite useful and quite powerful computation engine for the neural symbolic application in the future, which will be the next generation of the AI, right? So I just talk about like how big, how important the AI is and how Tenstorrent using the RISC-V technology for general purpose compute and also the AI accelerator. So everybody think AI is actually complicated, but on the high level, in the highest level of abstraction level, it's only 600 lines of code for Llama, right? You can download it from Tenstorrent, website, right? Our Llama code is only 600 lines, but it's actually super complex when you start mapping the 600 lines of code into the implementation of the hardware. And why is that? Because it has huge amount of data, right? The amount of data you have to process, right? Going through the pipeline, you have to process. Even if it's repetitive, you have to partition well. You're going through chain of different technology, right? Networking technology, computation technology, general purpose technology, operating software stack, everything, right? So I would say every interaction, right, among the different layers has to be very efficient to make this completely efficient. So I do this kind of calculation, right? So you can see that. So suppose we have 128 Tenstorrent AI processor, right? They contain the ASCON CPU we design. And then you were mapping from the highest level of the AI model running on the 1 kilohertz only, and then mapping to the PyTorch, right? So you run 1 megahertz, and going to different level of the abstraction. Eventually, you expand into, 64,000, general purpose, single CPU in the whole system. They have to synchronize together, and then move in the data and do the computation you like. That's where the complexity is. But you can see from going through this software stack, you can see also how the processor technology being applied in each of the section of the abstraction level, right? So the computation requirement is totally using the processor technology, which provided by RISC-V. It's very interesting for me. Right? So this is actually the breakdown, how you break down from the highest level computation to the detailed computation itself. So I really feel like the future AI technology will adopt in the RISC-V technology more and more. Tenstorrent is an assertion of such a technology, because we can imagine in the future when Tenstorrent move into autonomous driving market, consumer market, there will be a new requirement about the PPA for the AI computation. And if with the flexibility of the scalability, extensibility, efficiency, and also stability, Tenstorrent can use this technology to build in the AI technology for many, many different kind of product we like to build also with our partner. So that basically is my talk. Yeah, thank you so much.
Thank you very much, Mr. Lien. So now the discussion time. So open for the discussion. So any questions? So very welcome. So. No questions? Okay. Mr. Lien, would you come to the microphone? Yeah. The question was?
I actually, so the question is about like, can RISC-V technology apply to the mobile phone, right? So the key thing is actually the software ecosystem supporting the mobile system, right? So it's basically the Android operating system. So we actually are in contact with the Google, right? Try to moving the Android in the direction faster. The key important thing is actually China, right? China is starting branching out the Android operating system if Google is not moving along. China really want to independent, decouple the technology dependence from the other country, right? So if they branching out the Android operating system, doing their own and pushing that technology in the future, right? Google will lose billion of the business opportunity on that. So Google have to move faster. China in the future, basically what they'll do is that all the hardware solution will be open source hardware architecture, right? Because they want to decouple the dependency of the technology from the foreign country. So I think that's a significant moment. So can they be applied to the mobile phone? Once the operating system ready, nothing actually you can stop that. The most important thing is actually the PPA. Mobile phone is super picky about power efficiency, about performance, about area. And then that's more depending on, I come from Apple, right? So that's very depending on the microarchitecture choice you actually make, right? So the microarchitecture is actually determining the power efficiency area and then your implementation. So once that satisfies the customer demand and the software ecosystem is there, right, it will be available for us. And I expect that can happen in 3 to 4 years. Yeah.
Okay, thank you. So it's time. So please applaud him again. Thank you. So let's move on to the next.